is the story of how we figured out the secret of the universe. And it took several thousand years, but it's something that we now take for granted. This is the story of what led up to the little electric devices that you now possess. Section 3, this is atomic theory. This is how we started to learn what an atom looks like. First, there were some Greek philosophers around 2,500 years ago. Quite a while ago. And they suggested that if you took a substance and you cut it in half, and then you cut it in half again, and you cut it in half again, and you kept going, they suggested you would eventually get to a smallest piece. And they even gave it a name. They called it what word in English comes from that one, do you think? From the word atomos. Atom. They were ahead of their time. They were starting to realize that all matter is made up of these smallest particles called atoms. Except Aristotle, who was one of the greatest minds of that time, he said they were wrong. And Aristotle influenced philosophy and influenced science, and in all honesty, he probably set science and physics back by about 1,000 years. But he was very influential. He said, you know what? You're wrong. All matter is made up of different combinations of air, water, fire, and earth. You may have heard those things phrased together often in like a fantasy movie or a magic game or something like that. Earth, wind, air, and fire. There was a band called Earth, Wind, and Fire. He believed that everything was made up of different combinations of those four things. He was wrong. But for the next 2,000 years, everyone believed it because you could, through some clever experiments, show that that might be true. But it took some more clever experiments to show that that couldn't be true. So a little reminder, think for yourself. Don't trust anything I say. I could be wrong. In fact, Dan, most of today's lesson is going to be technically wrong, but it's a good model to help us visualize what's going on such a small scale that our brains can't comprehend it. Then along came alchemists. Can you see the word chemistry hiding in there? These are the predecessors. These were scientists slash magicians slash crazy people. Well, what they were trying to do was they wanted to turn lead into, you may have heard this. What did they want to turn lead into? Gold. Why lead? Because lead is really heavy and so is gold. So they figured maybe there wasn't much of a difference. And they figured, well, if there's different amounts of earth, wind, fire, and water, maybe I can somehow transmute this substance into another substance. Now, they were wrong. It's well, I can't quite say it's impossible to do that. Using their technology, it's impossible to do that. But along the way, they started to learn many of the rules of chemistry. They also discovered lots of new elements from the periodic table. And then we started to figure things out. The first person we want to talk about is John Dalton. Around 1800, so around 214 years ago-ish, along came John Dalton. And he showed why the alchemists had been wasting their time and why Aristotle was wrong. And while his theory has since been refined, we've added to it, he got scientists started in the right direction. Now here's what he said. In his model, atoms are solid spheres. What's a sphere? Tennis ball. So imagine a little tennis ball. As a picture on the next page for you guys, he said, here's an oxygen atom, well actually here's a hydrogen atom, and he said a hydrogen atom would look different from an oxygen atom. There, now it's orange, looks different. He said all different types of element atoms look different from each other. Now, he was right on that. What he didn't realize is they're not solid spheres. We can still go smaller. We're going to be talking about that today. So here's what Dalton said in his atomic theory. All matter is made up of small particles called atoms. So he stole the word from the Greeks. He adapted it. Okay. And he said atoms cannot be created, destroyed, or divided into smaller particles. He was wrong on this part. He was certainly right on the first line, good, and the idea that all different elements, an oxygen atom looks different from a hydrogen atom, looks different from a helium atom, looks different from a uranium atom. He was right on that. Then he said, all atoms of the same element are identical in mass and size, but they are different in mass and size from the atoms of other elements. He was right on that. Every hydrogen atom looks alike. Every helium atom looks the same. One is just like the other. Every uranium atom is just the same. Now, I'm fibbing a bit. Actually, technically, if they're radioactive, that's not quite true. But for the most part, every element looks like its own atom from its own element. Every oxygen atom looks as the same as every other oxygen atom. So far, he was right on this, wrong on that, right on this. And then he said, compounds, that's a terrible N at the end there, are created when atoms of different elements link together in specific proportions. He was right on that too. Does anybody know what the chemical formula for water is? You've probably heard this one. H2O. To make water, you need 2 hydrogens, 1 oxygen, and that's water. Not 3 hydrogens, not 5 hydrogens, not no oxygen. So he was right on that. He started to realize that how different elements combine and in what proportions determine what kind of a compound you can get. And strange things, oxygen is a gas, hydrogen is a gas. Put them together, liquid at room temperature. Table salt is sodium chloride. Sodium is fatal. Chlorine is fatal. Put them together, yum, dinner. 2 toxic substances become something we need to live. Y'all need a little bit of salt in your diet. Not too much, but a little bit. So, 3 out of 4. The problem, Dan, you gonna put your phone away? Or, oh, you weren't looking at your phone, my bad. The problem is that last one. Compounds are created when atoms of different elements link together in specific proportions. He was right, but he couldn't explain why. Why do I need 2 hydrogens for 1 oxygen to form water? And we will explain that in a little bit. Next came J.J. Thompson. So for about 100 years, 1800s, Dalton's model explained a lot. And then J.J. Thompson in 1897, almost in 1900, just before 1900, he discovered, right, negatively, yeah. Oh, don't use red, Mr. Dueck. Negatively charged particles. He didn't know what they were. Later, they were given a name. They were called electrons. Yes, from which we get our word electricity. What's electricity? All electricity is moving electrons through wires, and we're pretty good at it. But what he realized was these charged particles were smaller than atoms. So he realized that atoms were actually made of smaller particles. And not only that, he noticed that some of these particles were positive charged, and some of these particles were negatively charged. Now, we'll talk more about what positively and negatively charged means another day, but okay. So this is J.J. Thompson's model of an atom. He was wrong, but he was closer. He imagined an atom as like a chocolate chip muffin. How many of you have had a chocolate chip muffin before? Okay, so think round chocolate chip muffin, just so we have the shape right. And he said, in a muffin, the chocolate chips are kind of scattered all throughout. So he said the electrons, those negative charges, he figured those were like chocolate chips. They were spread all throughout the atom kind of evenly. Oh, and the dough was positively charged. So spread throughout a positively, or embedded in a positively charged ball, the rest of the muffin. Now, actually, muffins are what we eat today. J.J. Thompson was from Britain in 1897, and their big snack was plum pudding. So he, instead of imagining a chocolate chip muffin with chocolate chips, he imagined pudding with plums all scattered through it. So it's often called the plum pudding model. And it's closer. And there's kind of a picture to help you visualize it. Okay? Atoms have smaller particles called electrons, but what he didn't yet know was where they were. This was his hypothesis. Oh yeah, turn the page. Put your pencils down. So a short video basically repeating what I just said. You're teenagers, I need to repeat stuff. There you go. Next page. Ernest Rutherford. From New Zealand, but he did his best work in Montreal at McGill University, so we got some good Canadian content here. He's often called the father of nuclear physics. And he was a student of J.J. Thompson. Can you kind of see the tree of science that's kind of growing here? So, he did a very, very famous experiment. Jordan, you can expect to have this experiment have to describe it on a test or a quiz. And I'm going to be flogging this experiment for the next 20 minutes or so, and I'm going to be talking about it over and over and over and over and over. Proud Canadian moment. Did this at the University of Montreal. In fact, I think the room that he did this experiment in, I'm pretty sure there's a memorial plaque because, holy smokes, this opened up nuclear physics. What did he do, you ask? What did he do, you ask? What did he do, you ask? I'm so glad you asked. In 1909, only about 10 years after Thompson had discovered the electron, he exposed a very, 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 very thin sheet of gold foil. And literally, they just pounded it really, 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 really thin. Gold is very malleable, which is one of the reasons we use it as a metal of preciousness and decoration. With a hammer, you can pound it so that it's only a few atoms thick. So by very, 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 very thin, I mean really thin. He exposed it to a stream of high-speed, heavy, positively charged particles called alpha particles. Show you a video in a second. These alpha particles were heavy, they were fast. Think firing a bowling ball out of a cannon on a bigger scale. So on the atomic scale, it was like firing a bowling ball into the fog, not knowing what you were going to hit. Then he put a detector around the gold foil, and it would click for a split second whenever an alpha particle hit the detector. So here's the setup. Okay? He's firing these heavy particles through this very, very thin sheet, and he noticed almost all of them went straight through. So the first thing he said is, okay, there must be lots of space between the atoms because I'm not hitting the atoms. I seem to be going between the gaps between them. But every once in a while, click, these alpha particles would rebound off something inside the foil, inside the atoms. Sometimes they would bounce sideways, but sometimes they would bounce completely backwards. So now we're going to hypothesize and see if we can come to his conclusion. Let's imagine that you are shooting a cannon into the fog. But let's imagine it's a cannon that can just go boom, boom, boom. It's like a machine gun cannon. It's firing bowling balls like a machine gun over and over and over and over. And you let it run for 30 minutes. And you notice the vast majority of the bowling balls just keep going and don't hit anything. But every so often, a bowling ball comes bouncing back out towards you. What might you suspect is in the fog that could do that? This was his question. He started to say, wait a minute, what the heck could be inside an atom that could do that? Now, the first thing he said, I'm firing bowling balls, I'm firing alpha particles. They're heavy, so for it to hit something and bounce back, what could you tell me about that something that it's hitting? Heavy or light? Yeah, heavy. Really heavy. Really, 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 really heavy. So the first thing he said is, there's got to be something really heavy inside atoms that we don't know about. With me? Except I'm barely ever hitting it. In fact, he found only about 1 in 1 million shots hit it. So if you were firing this bowling ball into the fog, and you were only hitting something once every million shots, what could you conclude about the size of whatever it was that you were hitting? Is it really, really big and easy to hit? No. What is it? Unfathomably, unimaginably small and heavy. He had just discovered what we now call the nucleus of an atom. So instead of J.J. Thompson with his electrons all scattered everywhere and the positives kind of like this dough, what Rutherford was discovering is there was something inside the atom, very, 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 very small, and relative to the atom itself, very, 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 very heavy. It's a good piece of reasoning, and you guys were able to reason to the same conclusion. Had you been there, you would have been able to discover the nucleus had you run this experiment. But he was the first one to run it and interpret the results properly. So let's write this down. Going to come back, but I want to get the conclusion. Hand up. Stretch. So the results showed that most of the alpha particles went right through. That means atoms are mostly empty space. Oh, this made sense because an atom is made up of mostly empty space. However, he was astonished to see that some alpha particles deflected. They hit something. And because these alpha particles were so massive, think really, my bowling ball analogy isn't big enough. Think like firing, I don't know, cars. Like these alpha particles were huge, and they were bouncing off something, and not just barely deflecting, some bouncing straight back towards the detector, which meant whatever we were hitting was really, 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 really heavy. Why? How do we know that they're really, 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 really heavy? Alpha particles were heavy too. And for something really, really heavy to bounce off something, that other thing, you've got to be pretty heavy. Otherwise, it would have just barely deflected or grazed or glanced off. But they bounced, some of them, straight back. And this mysterious object must also be really small. Why? Hardly any particles hit it. The vast majority, 999,999 out of a million, went straight through. Couldn't hit it. So what had he discovered? The nucleus of an atom. The very, very tiny, very, very dense, very, very heavy, positively charged center of an atom. He wasn't done. A decade later, he actually showed that inside the nucleus there was two different kinds of particles. One was positively charged, and he called it the proton. And one had no electrical charge. And when something has no electrical charge, the electric term for that is neutral, so he called it the neutron. And there we had it. We had now the three subatomic particles that make up an atom. What we didn't yet know was how the electrons were structured. We knew they were there, we just didn't know how they were organized. Well, Thompson had Rutherford as a student. Rutherford had a student named Niels Bohr, one of the biggies as well. And here's what he said. This is the Bohr model of an atom, and this is what we currently believe is as good a model as anything else. He said that the electrons surround the nucleus in specific energy levels or shells. By the way, in the US and in old textbooks, and when your folks were in science, when I was in science, we used to call these orbits, but that's wrong because it suggests that these shells are circular and that the electrons are circling the nucleus. They don't do that, so we're not going to use the term orbits, but I may show you an older video that still uses that term, or if you talk to your folks about science, and why would you not talk to your folks about science? It's science! They may talk about electron orbits, but we call them shells or energy levels. So shells it is. What did he say? He said that the electrons surround the nucleus in different shells, but each shell can only hold so many electrons. The first shell can only hold 2. Once you have 3 electrons, you're on the next shell. The second shell can only hold 8. The third shell can only hold 8. The fourth shell can hold 18 electrons. The fifth shell, hang on, put your pencils down, look up. So neon lights are a great example of this. When electricity is added to neon gas, the electrons in the neon atoms pick up some of the energy from the electricity, and they jump up to a higher energy level. For them to get back down to their original shell, their original energy level, they have to get rid of that extra energy somehow. How do they do that? They give off a photon of light. It's really pretty simple, not high tech, just clever. Nearly done. So, inside the atom then, this is what we now believe. You know what? This is what we now know. I won't even use the word believe. We know this is true. So, the atom is the smallest particle of an element that retains the same properties of that element. What are the atoms? They're all listed on that periodic table, and you'll all get your own copy. There are 92 elements that appear in the universe in nature. And then in labs, we're able to create about another 20. But we now know that there are smaller particles that make up every atom. We call them subatomic particles. Smaller than atoms, subatomic. Question, Jordan? Can't read my writing? Because that's fine. My writing's messy. Which word? Subatomic. So subatomic. Sub meaning smaller than, atomic meaning from an atom. So smaller than an atom. What are they, Kiana? First one. Proton, which is positively charged. Instead of writing positively, can I just put a plus sign? We have the neutron, which is neutrally charged. You know what? No charge, has a charge of 0. Not negative, that's not 0. But you can write a 0, and I usually will. Then we have the electron, and the electron is negatively charged. Now, protons and neutrons and electrons all have mass, but the protons and the neutrons have way more mass than an electron. So much so that we're going to pretend that electrons have no mass. They do, but it's literally 30 zeros before you come to the first digit after the decimal place. So it's so close to nothing that we're going to ignore it. So, key ideas. Protons and neutrons contain most, in fact, almost all of the mass of an atom. 99.9999999999999 25 more nines % of the mass. But not 100%. I gotta, nerd, I gotta be honest. Nearly there. Electric charge comes in 2 types. Positive and negative. Which subatomic particles have a positive charge? What did we just say? Which subatomic particles, neutrons, protons, and electrons, which ones have a positive charge? Protons. Protons are positive. Protons are positive. Protons are positive. Mr. Dueck, is there an easy way that I can remember that protons are positive? I suck as a teacher. I got nothing for you. Hopefully you figured it out, yes? Electrons have a negative charge. Neutrons have no charge. They're neutral. Neutrons have no charge. They're neutral. Neutrons have no charge. They're neutral. I got nothing there. Maybe you might come up with a clever way to remember that. So for protons and electrons, each of their charges has the same size but opposite sign. In other words, in math, if you add 1 plus -1, what is +1 plus -1 in math? 0. If you add 1 proton to 1 electron, you also get a charge of 0. Fancy word. Neutral. Almost done. I like this chart. I like this chart. I like this chart. This chart would make a great question. Why did I say that? Did you hear me say it's going to be on the test? You're one of those students that notices when a teacher tends to emphasize certain things. You're a good student? Okay. What would be a good letter to use as an abbreviation for a proton? fact, what we do is we use a lowercase p with a plus sign to just emphasize that it's a positive, also to show that we're talking about a proton and not the letter p. So the symbol for a proton, p plus. What would be a good symbol to use for a neutron? In fact, we go lowercase n 0, because that's the charge. What would be a good symbol to use for an electron? So for the rest of the year, E with a negative, you do not have to write those words out on a test or in your homework. If you write P+, I'll know that you're talking about a proton. I won't mark it wrong or anything like that. Or if you want to use those abbreviations, knock yourselves out. They're great. Go ahead. Okay. What's the relative mass on a proton? Now, these are measured in what are called atomic mass units compared to an electron. So if an electron weighs 1, a proton weighs 1836, and a neutron weighs 1837. I'm not going to make you memorize this line. What I want you to realize is protons and neutrons weigh almost the same amount, and they weigh way more than an electron. Almost 2,000 times more. So which is heavier? Protons and neutrons. Which is lighter? Electrons. How much does a proton weigh compared to a neutron? Almost identical. Close enough that they're identical. What's the electric charge on a proton? Proton is what? What about a neutron? Careful. Zero, no charge. What about an electron? And by the way, I'm glad Aiden did that, because that's the most common mistake. Kids go, neutron negative. No, sorry, the ends don't work there. Electron, you have to memorize, is negative. The proton is located inside the nucleus in the center of an atom. The neutron is located inside the nucleus. That one's not too hard to remember. The neutron is in the nucleus. And the electrons are located in shells outside the nucleus. Yeah, okay, I can finish by noon and give you 15 minutes to work on the homework. Sorry, this lesson's gone a bit longer than I wanted to. The nucleus. It's a tiny, 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 tiny region in the very center of an atom. Center is spelled R-E in Canada, E-R in the U.S. I'm a proud Canadian, so I'll spell it right. I also say Z. It's really, 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 really small. That's what Rutherford's experiment showed us. The fact that almost all the alpha particles went straight through said whatever they're hitting, it's small because barely any of them are hitting it. You know what? It's mind-bogglingly small. I'll show you a video either at the end of this class or the beginning of the next class to try and help you wrap your brain around it. It's mind-bogglingly small. You're not looking at your phone or anything, are you, Hudson? No? Sorry, my bad. I saw you looking down. I apologize. False alarm. It's always positively charged. Why? What particles are inside the nucleus? What did we say on the chart right above? Which particles are inside the nucleus? Protons. So the nucleus is always positively charged. The neutrons have a charge of 0. 0 plus positive, still positive. And every element past hydrogen also has neutrons in its nucleus. Hydrogen, the most common element in the universe, its nucleus only has a proton, no neutrons. After that, there are always neutrons cohabitating along with the protons, kind of glued together. Protons and neutrons are held inside the nucleus, and normally they can't enter or leave it, although in labs with particle accelerators and particle smashers, we can. You guys have been patient. This is science. Oh, by the way, in situations where protons and neutrons do leave the nucleus, this is boom. All the atomic bomb was finding a way to split the atom so that protons and neutrons, because they're held there by energy, broke apart. That energy had to go somewhere. It went out in the force of the biggest explosions in history. You don't need to know that, but it's nerdily cool and terrifying. Last bit. Electrons occupy special regions called energy levels, or our word of the day is shells. Electrons account for the region they occupy, accounts for almost all of the volume of an atom. So if this is an atom, what you would be seeing is almost all electrons. If this was an atom, the nucleus would be so small you couldn't see it with your eyes. Almost all of the volume of an atom is taken up by these electron shells. Electrons have very, very little mass, but they have most of the volume. They take up most of the space. Okay. In fact, if I really want it to be fun, I think I looked it up. It's 99.99%, so almost all. For those who like the math numbers. Each electron occupies one whole energy level at a time, so it's not like a planet orbiting around a star. The electrons aren't whizzing and whizzing and whizzing and whizzing around. In fact, even electrons themselves, they're sort of like clouds of charge more than particles. You guys good? Almost done. So we don't use the word orbit anymore. It's more like a spread out cloud of negative charge that exists in the whole region at all times, but it's actually way stranger than that. If you're bored, if you're a science nerd, sometime do a YouTube search for quantum physics explained and be afraid, because on the subatomic level, stuff behaves in ways that makes witchcraft and Harry Potter look normal. Doesn't behave that way on the big level, but electrons do weird, freaky stuff. Hustle back. I'm going to give you the homework to work on, and then I'm going to put a video. You can watch the video or work on the homework or do both, but until the video is over, no headphones or talking, okay?